Okay. So let's go back here to stochastic processes that we had begun. Stochastic processes, um, again, to be honest, is a difficult topic for me too, because um, I've never been very uh, attracted to stochastic processes somehow, because I was trained to do memory studies, okay? uh, which is what we did in the beginning. We have done, that's why your homework is on memory function. But when there is no memory, that is stochastic limit. And so when I first got familiar with stochastic, first got to learn about stochastic processes, it was, I had become a full professor. I mean, I looked at it before that, but nothing serious enough to teach. I'd become a full professor and I had a student called Linda Shanahan, and Linda was trained as a civil engineer and a mathematician. She had a BS in civil engineering, she had an MS in applied mathematics, and Linda had worked as an engineer for about 28 years at the time. She was a few years older than me. And she came to study, to do a PhD with me, and she and I were working on battles at the time. She was a very, very smart woman. And so Linda said, can I do this problem using Markov chain approach? I knew what Markov chain was, and I was not very enthusiastic about it because I wanted more interesting results than what Markov would give. But Linda said, I'd feel very comfortable if I do that because I've done it. My thesis was on it. I'm pretty good at it. So I'd like to analyze battles with Markov chain problem. So I said, fine. I said, I have no problem. It's your job now to teach me because I have forgotten most of the stuff. So Linda did the work. Linda taught me, and we wrote a paper on it and all that. And actually, maybe I should bring up that problem uh, on the Thursday lecture. Oh, Thursday lecture, Tony, there is an issue. I said we'll meet after, but we have a colloquium speaker, Laura Smilowitz, and I'm supposed to meet with Laura and go to the talk. So we can talk today after class, that's okay, or we can even talk tomorrow if you have time, whichever works for you. Okay. Um, anyway, so I'll talk about that problem that we did as a real world example of how we can take off from this problem. But let's go to what Markov problem was. I'll kind of summarize it for you so you don't get bogged down with the details. In general, the probability of something happening um, can be analyzed in many ways. Probability of the event happening right now at time t. You can ask this question. What is the probability that there'll be a thunderstorm today, right? At 2 o'clock? That may be your P1 of psi and t. That will be a P1 of psi and t because you have just asked the bare question, probability of thunderstorm happening today at 2 o'clock. P2 would be a probability of thunderstorm occurring today at 2 o'clock, given there was a thunderstorm yesterday in the afternoon. That's P2. P3, more, blah, blah, blah. So you can see the whole idea. The idea of stochastic analysis is the thunderstorm happening today, given there was a thunderstorm yesterday. That's pretty much where the buck stops. It's the immediate past that's what matters. So this is what, when we talk about stochastic analysis, this is what we actually mean. That's the whole point of all the words that we have put together here in this slide. Okay. And the other point also, which I think is fascinating, is what's the probability of thunderstorm happening today, given there was some probability of thunderstorm happening yesterday and some probability of thunderstorm happening the day before, blah, 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 all the way till the beginning of the formation of the planet. So this is your P sub n, n going to 4,700 million years, right? Now you can say thunderstorm happening today, given the history of what has happened before. Everything is on the right side of this bar. Times the complete open probability of this one minus taken away from the 4,700 million years. Anyway, this is not a very important step here, but the most important step that I think that we get to is literally coming to some kind of a statement like this, which we call the Markov assumption. The idea of a Markov assumption is quite a powerful statement. First of all, it generally should be viewed as a non-equilibrium process. So what is the probability of thunderstorm happening today, given the past history of the planet, that is on the left-hand side? What is the probability of the thunderstorm happening today, given yesterday? So that's one 2-point probability, multiplied by probability of thunderstorm happening yesterday, given day before yesterday, another 2-point probability, multiplied by thunderstorm happening day before yesterday, given what happened day before yesterday, another 2-point probability, all the way till the very first instant in time when the planet started functioning, which is your P1, J1, P1. Now here you have a choice. When the planet started functioning, do you assume the planet can be taken to be at equilibrium, or do you assume that the planet had very wild conditions? Because then there may have been 77 thunderstorms in 24 hours. Or it may have been an extremely tranquil day. So this very first instant now provides you with a choice. You want to take it as a non-equilibrium problem, or you want to take it as an equilibrium problem, as here, where you take away the time because you insert the explicit assumption that wherever the process begins, things began from equilibrium. So there is a distinction, therefore, between the statement here. Let me take a pencil. Between this statement here, where we have this guy, versus this statement here, where we have this guy, where there is no time. Big distinction. Everything else is the same, but that's where our distinction sits around. So when we talk about a Markov process, I think it is sufficient to simply remember for the long term, basically this part. This is the crux of the Markov process problem. Now we move to an equation situation. This is not really an equation situation. This is a definition situation, where what we have on the left side is definitionally being explained on the right side. Right? So it's not really an equation. In fact, I'd be a little bit more comfortable if I put this here and if I put this here, although that's not in the books. That's what I really mean. But here, on the other hand, we are introducing something which we are calling this Chapman-Kolmogorov process. And this Chapman-Kolmogorov equation, which is describing whatever is going on here, is very interesting because it is fundamentally different than what we had here. Here what it says is, how exactly did this process, any one of these processes, how exactly in general, can this process be possible? That's really what is being asked. And for that reason, it is framed with just one index k here. It's just one index, this k. And there is also one index L here. And you see it's summed over all L's. L equal to 1 to k, L equal to 2 to k, L equal to 3 to k. In other words, in how many different ways can you perceive this state coming to being, this k t minus t prime. T minus t prime is, of course, nothing but time, and implicit in it is just the fact that the beginning and end points matter. The detail of the time doesn't matter. If it's 2 hours apart, if it's 3 minutes apart, that's all that matters. But which 3 minutes, that doesn't matter. It's 303 to 306 or 703 to 706, doesn't matter. So this is a very obvious statement. It basically says that the way time flows as far as this system is concerned, there is not that much history dependence. That's what it says. It's not like there was a battle that was fought between L to K and that battle's importance is entering. No, nothing traumatic, dramatic happened. That's all it said. So L to K, L can be many states. And it is the sum of all these states, pathways by which you can arrive at K. And not only that, to make matters even more clear, this term outside the curly brackets, this term is saying how it got to this Lth state to begin with, starting from the initial Jth state. So J to L, L to K. J to 1, 1 to K. J to 2, 2 to K. J to 3, 3 to K. Blah, 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 blah. And everything is happening between T minus T prime. T and T prime are fixed for this particular case. And of course, it's implicit that T prime is an intermediate time between T equal to 0 and T equal to T, as it should. And no wonder it's called a chain equation, because it is, of course, a chained process, 1 to 2 to 1. So the important thing to remember is when we say we are writing the Chapman-Kolmogorov equation, we are actually describing rate processes. Any rate process we can do. For example, let's say a rate process like, I'm traveling from city A to city B. City A to city B, I can travel in many different ways. And all those different ways would be incorporated here in a certain time window. Let's say my time window is 5 hours and 5 hours. It's like that, simple enough. Now the next thing that is done, and this is a big jump, is that now this in general is a nonlinear equation because there is no real clarity on the process. So in general, this is a nonlinear equation, but it can be made into a very simple linear equation by thinking about this process in terms of a rate. So some kind of a rate of the probability happening within so and so time, unit time. Okay, probability of J to K happening in unit time delta T. That's what this W of K and J is. So it's like a frequency for that reason. It's like a frequency. So it's like a frequency. So now what happens is, we know from physical perspective that if you are looking for ddt of P, how P is changing in time, which is of course a little bit more detailed information. It's not like just P of KT only, but it's how P of KTJ is actually changing in time. If you want this information, so dp dt if you want, first derivative level information, Then you need to calculate not only that there's a process probability of going from L to K, but there is also the reverse probability of it falling back from K to L. That can also happen. A transition can happen quantum mechanically from state one to state two. And then again, for whatever reason, it also has a finite chance of coming back from state two to state one. And of course, if there is a chance of it coming back from state two to state one, then ultimately at the end of the process that takes time dt, you want to be able to incorporate that. So what's the probability it was in state L to begin with? What's the probability it was in state K to begin with? That also needs to be incorporated as done here. So therefore, this is the linearized Chapman-Kolmogorov equation, or what we commonly refer to as a master equation. Typically, these are called master equations. Master equations are very good equations. They talk about rate of change of something, basically in terms of minimally two processes. One is a process of A to B, and then there's a process like B to A. That's what master equations are. So, for example, you have a gas. Gas particles are colliding. So, because of collisions, particle one hits particle two, but there is also a probability of particle two hitting particle one. It's like that. So, energy. There's one process like that. Then there's this two hitting one is also a possible process. So one can, if you think of it in terms of transitions, something like that can also be used here to take care of collisions between particles 1 and 2 in the time window dt, let's say. And then if you can integrate over dt over all the possible time windows. There is something further that can be determined here. The possibility of what you have in the square brackets here should ideally be a positive number or should be 0. It should not be a negative number. Okay, because the goal is to get to K. So L to K, and there is a finite chance of jumping back from L to K, but finite chance of jumping back from K to L. But K to L, implicitly in this physical process, is not designed to be larger of a probability than L to K. L to K is the main thing. So K to L is a secondary process. Now, that is not evident in the way the equation is stated. That is only evident when you bring in that part of physics. So that's important to keep in mind. We are actually, this is why these problems are often not places where mathematicians do a lot of work. Because for a mathematician, this would be very traumatizing if we say that you can only go from L to K, and that is the dominant process, and the opposite cannot be a dominant process. You see, this kind of statements really bother mathematicians because they would say, why not? You are setting up the problem. You must allow for both possibilities. Then you see you have so many dividends that you can get out of it. But typically we are weirdos. We say, no, we don't care about that. We only care about this. Leave us alone, right? So the functionally we operate very differently. Anyway, but you can see immediately that because you are traveling from L to K, and then from opposite can happen, you actually can have a matrix type situation here because K and L, they both will be running over the same set of indices because they pertain to the same system, right? So they'll be running over the same set of indices. So therefore, intrinsically, you are talking about some kind of a matrix type equation. So that's what brings us to the next stage of the problem. In the next stage of the problem, observe that we are talking about just pkt of J, just this thing. Conditional probability, just this thing. However, here we are actually talking about the sum. talking about the whole sum. And of course, for the whole sum, the probability is going to be 1, right? All probabilities added up is going to be 1, which means the moment you do a DDT of the whole sum, you'll get a 0. So therefore, it is very, very clear that this statement here, 0 equals DDT of sum over k equal to 1 to n, P of k and t and j, is just a 0. It's just obvious. However, the fact that you have written it as a sum, and the fact that you can make a statement like this has a dividend. What is the dividend? The dividend is you can now think about this P of t, not P of k of t, P of t as a column vector. Or alternately as a row vector. You can think of this as a column vector. Suppose that the system was in one particular state after the transition. Suppose the system has come to the kth state as we see here, P of k of t comma k of t bar j. Suppose kth state j to k has happened, j to 1 hasn't happened, j to 2 hasn't happened, j to n hasn't happened, only j to k has happened. So if you now think numerically for all the probabilities in this column vector, it's k comma t vertical bar j, that probability will be 1, but every other probability will be 0. Right? Every other probability will be 0. So that's how you think about it. But the powerful thing is that this kind of matrix formulation of the problem actually allows you to write this rate equation, this master equation, as a simple equation like this, a matrix equation like this. That's what it allows you to do. So all of a sudden, you have this matrix equation that has now become possible to not take into account only one process, but to take into account everything that is going on in the system. It can be a highly composite system made up of 5,000 particles. So all of the 5,000 by 5,000 possibilities are incorporated in your square matrix W. P itself has 5,000 elements in your column vector form. You can put the whole thing there. Now, yes, it is convenient, but unless you can make some nice approximations or nice physical connections, you have just invented a lot of work for yourself, right? So you have to be now very careful as to how you approach this problem. So the first important trick that we had learned about that you probably don't remember is that if you go back and look at the previous slides, in particular, let's say this slide, we don't have any journey from J to J, because that means nothing has happened, right? J to J, nothing has happened. However, from a matrix manipulation point of view, it would be convenient to have a J to J, because otherwise you have to put out this nuisance of K not equal to J every time you do something. How will you write a matrix with that condition in a general form? There are all kinds of silly issues that come because the diagonal term of the matrix is by definition missing. So what you say is, I will make up the diagonal term to be, let me add a red term, to be this entire negative term. I'll make this my diagonal term. Nobody can argue with that. You can make your diagonal term whatever you want as long as you don't change your equation. And the equation remains thoroughly unchanged if you make that guy your diagonal term, right? The moment you make that your diagonal term, then voila, then you come here, right? Then you can basically say k equal to 1 to n wkl can be written as this piece, which you already have, and then this WLL piece, and this WLL piece is defined here. Actually, this is not the best way to do it. The L and K is a little bit complicated here. So this is just a negative term, that negative term that I showed you, which was right here in red. So this stuff is not going to be in the physics for the politician or the grandma version of the lectures.
We hope.
Okay, so there we go. So you see, this is again writing the same thing. Actually, I think this one, I've done something goofy with the notation. This should be the other way around. Anyway, don't worry about it. Don't change anything now. Basically, it's a set of negative terms. Now, here is an interesting thing that k equal to 1 to n wkl, L to k that is, with the positive and the negative terms combined, the entire row of the matrix actually sums up to 0. That's the way it's been defined. So this is the column. I'm sorry, this is the column sums up to 0, not the row. Row is fine. The column sums up to 0. So you have to write down the matrix a little bit and look at the rows and columns carefully. And you will find the way it's set up, the column sums up to 0 because column sums over all the k's. So that's like the 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. So in general, 0 is a non-trivial eigenvector of the problem. And W of PT is equal to 0, which implies dPdt is equal to 0. So there are some very, very nice properties of this master equation that emerge. But most importantly, the fundamental property where it all comes from is that this diagonal term is a purely invented term to take into account the negative terms that you have for each process. So this is not a symmetric matrix, right? This is a matrix with very, very different kind of properties. It's a square matrix, but W12 is not W21. W13 is not W31. W23 is not W32. Okay, these are not at all the case. It's not necessarily a symmetric matrix. If it's a symmetric matrix, that would be another layer of specialization that is being thrown onto this matrix. Not only that, there is another very interesting physical part of the problem. In general, because of the structure of the problem, the formal solution to your P of t is basically e to the WT of 0. Because of the, let's go back and look at the form of the equation itself. This is the form of the equation, right? dp dt is wp of t. And we were talking about the W matrix, but this is the form of the equation. dp dt is wp of t. So this is a first order equation. So this can be trivially solved. P of t is e to the wp of 0, e to the wtp of 0, I'm sorry. Just like the Liouville equation. Same thing. So this equation then, the solution of this equation here is p of t is e to the plus w of t p of 0. Let's see if I can delete this. Right. Here. Delete it. So we have, this is how formally our solution looks like. So therefore, to understand P of t, W is a whole matrix. What we need are the eigenvalues of the matrix. So here, for example, P of t is e to the plus lambda I of t p of 0. But these lambda i's are the n eigenvalues of our n by n matrix in general. If you have a 2 by 2 matrix, you have lambda 1, lambda 2. If you have a 3 by 3 matrix, lambda 1, lambda 2, lambda 3, and so on. But there is something very interesting about this problem. Our problem is one of probabilities. And probability P is not an unbounded quantity, right? It has to be between 0 and 1. So that implies that P cannot go to infinity, obviously. Now, if P cannot go to infinity, that means my lambda I cannot be a positive quantity. It can be an imaginary quantity, but it cannot be a positive quantity because that would yield something that would be unphysical. So I find this matrix personally very fascinating because I've never seen a matrix like this, where you get a constraint on the eigenvalues, and instead of boldly claiming eigenvalues are positive, here on the other hand, eigenvalues cannot be positive. They have to be negative. Eigenvalues don't even have to be real, they can be complex. Although there are limitations set by the fact that probability has to be a real number and probability is bounded between 0 and 1. We know that this can be a system with a very large number of particles in principle, large number of pieces in principle. They can be human beings, for example. They can be kangaroos. Anything can be put in the material in the columns. And probability is again between 0 and 1.
So what do these eigenvalues mean?
The
If we try
eigenvalue
to
meaning
think
is
about
very simple. The eigenvalues are simply telling you the evolution of the probability proceeds in what way. So for example, if lambda is 0, that means there is no evolution. That means there is a fixed probability which is time independent. But if lambda is a finite number, then that describes your evolutionary probability through that e to the lambda t, lambda I t term. That's what it means. I mean, think about a concrete example. You have 30 street dogs in your street. Actually, in the street we live in Pune, there are about not quite 30, but let's say about 10 or 15 street dogs that live around there. Okay, they are guard dogs. They are self-proclaimed guard dogs at night. It's a very peaceful street, but what used to be a super peaceful street has now, over the course of development of the city of Pune, which is what, 10 million plus now, or maybe more than that, has become by default the connection between a very major thoroughfare, very major road, it's called Pod Road, and the other is a sub-major road, meaning that the other side is also a major road, but it's not as major as the one street over, which is as major as this Pod Road. It's called Curve Road. So if you look at the map of Pune, you will see that Pod Road and Curve Road are two major thoroughfares. They're like the Champs-Élysées of Paris, both of them. So we are connecting effectively these two big roads. Not much traffic at night, but surely some cars pass by. A few people may be walking around. There are students that live there. There are universities nearby. So I've noticed, for example, that these guard dogs their behavior have changed. In the past, before this became so busy, these guard dogs behaved a little bit differently. If they found one person or one car, they would bark the heck out of that particular entity. Now, on the other hand, they are much more tranquil. They've got very, very used to the traffic around. Unless there is a highly suspicious person or a highly suspicious vehicle, they almost don't bark. There's like a woof. Okay. Otherwise, there was a massive chaos. So you can, for example, hook up this problem to describe the behavior of your guard dogs in the street. Okay. The behavior, there's 100% probability of barking. Now there is probably a 30% probability of barking. The probability of barking has gone down because the W matrix associated with the guard dog problem has changed fundamentally. Okay. So of course your W matrix in this problem is not time evolving. W is time independent. So in our guard dog version of the problem, the W matrix will actually have some time dependence in it. So you might actually need a slightly higher order equation. But you can think of it in concrete forms and begin to understand, try them out and begin to understand how they can be useful. But they can actually be extremely useful. There's no two ways about it. Now, the other very cool thing that I taught you guys, which I did not know about before I actually stumbled upon this topic a few years ago to cover in my StatMech class, is this Gershgorin's theorem. This Gershgorin's theorem is a pretty cool theorem because Gershgorin's theorem concerns the calculation of these eigenvalues. Now, we all agree that if you're given an n by n matrix, and if n is more than 2, then the calculation of the eigenvalues is a non-trivial task because it requires you to solve an equation which is beyond a quadratic equation to get the eigenvalues. So it could be a cubic equation, which in itself is bad news. Then you can end up with a quartic equation. Anything beyond a quartic equation anyway becomes really awful news because we can't solve them. So Gershgorin's theorem comes to rescue. Gershgorin's theorem tells us that, look, even if this is a relatively complicated looking n by n matrix where n is 30 by 30, don't be so worried. You may not be able to know the exact eigenvalues, but hey, does it really matter? You get more or less the approximate eigenvalues very quickly. And if you get more or less the approximate eigenvalues, maybe that's enough. Or maybe once you have the approximate eigenvalues by trial and error, you can perfect them. So that is the power of Gershgorin's theorem. So the statement of Gershgorin's theorem is that you are supposed to add up the moduli of all the matrix elements other than the diagonal elements in each row, for example. For example, of course, for an n by n matrix, you'll have n solutions. which means each row should ideally give you one solution, right? So each row can be attached to one eigenvalue. So now let's take the first one here, the first row here. So mod A12 plus mod A13 plus da 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 plus mod A1n. This whole gig is going to give you a positive number. Let's say the number is 5. Gershgorin theorem says, now you take A11, which is the diagonal element, make that the center, and draw a circle of radius 5 about A11. And Gershgorin's theorem further says, by the way, it applies for both rows and columns. We are just doing it for rows. And Gershgorin's theorem says that, you know what? The eigenvalue associated with this particular row in this case will be either on the circle or inside the circle. So if you don't have big numbers coming out of this matrix, you are bounding your values of the, bounding your eigenvalues pretty tightly. So if you normalize the problem in such a way that your A's are not large numbers, you are able to get pretty good boundedness out of it without doing any calculation. And by the way, in general, the matrix elements can be complex numbers. So here, for example, I've tried to draw a cartoon of drawing a circle around A11, drawing a circle around A22, and lambda as real and imaginary parts and so on. It's a very nice theorem, I think. My regret in life is most of the nice things I've learned later in life. If I knew them earlier, it would have helped me more, but I did. That wasn't the case. This is again the Gershgorin theorem being put in a way to please the mathematicians, but this is a more useful format here for me. So suppose you now take a 3 by 3 matrix looking like this. Here you can see A11 is 4, A12 is 1, and A13 is 0. So the radius of the circle, since the radius of the circle doesn't include the diagonal term, so 1 plus 0 is 1. So at plus 4, so you can see at plus 4, there is a blue circle of radius 1. So operationally, that's what it means. Similarly, if you go to second column, diagonal is at 0 and 1 and 1. So the circle radius now will be 2 because A21 and A23. But A22 is 0, so at the center there's a circle of radius 2 because 1 and 1 is 2. And likewise, here at minus 4, the radius of the circle will be 1. So these are the 3 circles that do not overlap. So the eigenvalues are contained within those circles. They can be either at the circumference or somewhere inside. And of course, if the circles begin to merge, then you can also say that the eigenvalues may have some possibility of merger also at certain values. There is a theorem here, for example, disjoint disks. If a union of k disks is disjoint from the remaining n minus k disks, then the union contains exactly k eigenvalues counting multiplicity. It's a very powerful theorem. Here is another example that I don't know which numbers I was trying out here, but here the way they were, there is these circles sit on top of each other. And these are the centers. This is the center. This is the center of this circle. That's the center of that circle. And that's the center of the bigger circle. So all three of them converge at the origin. So this also becomes a solution, I think, the origin in this problem. So Gershgorin's theorem is a good thing to have. Now, a little bit more can be done with the Gershgorin theorem problem. For example, here you write the matrix as M. The M operating on the eigenvector u is lambda times u. Lambda is the eigenvalue. So here, for example, the way you do it is to understand the structure of the eigenvalues. You pick the largest value in the eigenvector. So in the u eigenvector, let's say uk is the largest magnitude number here. So here this guy is the largest value. And the reason why the largest value is being picked up is because now what you do is you are actually writing this eigenvalue matrix eigenvalue equation in explicit form. So j equals 1 to n mkj. So mk1, mk2, mk3, all of these, and then u1, u2, u3, the entire column vector comes in. Is the eigenvalue lambda times uk. The next step is that you segregate out the diagonal term kk and dump it on the right side. So mkj uj, when j is not equal to k, this part is now lambda minus mkk times uk. This is the structure that you get. Now, once you get this structure, we are now in a position to actually figure out a little bit more about the eigenvalue, because the lambda is the eigenvalue sitting here, you see. You can figure out a little bit more about the eigenvalue. Unfortunately, I drew it on top of the bracket, but this is the lambda here, which is sitting on top of which is on the eigenvalue. So now what you can do is you can take out this lambda minus mkk piece, this piece here. Oh, this is too light. Let's use a red. One sec. Red. You can take out this piece. So this piece, modulus of this piece is then mkj uj divided by uk. Uk is the largest eigenvalue. It can never be 0, right? So you can divide by uk. So you divide by uk. It also guarantees that this term is less than or equal to 1. So this is the other guarantee that you're going to get. This term is less than or equal to 1, this term here. So now, lambda minus mkk. What is mkk? Mkk is the diagonal term. So lambda minus mkk is less than or equal to j not equal to k mkj. What is it telling us? Going back to Gershgorin's theorem, it's only telling us Go back here. It's only telling us that the eigenvalue sits inside the radius. That's what it's telling us. Because this is lambda minus mkk, this quantity here, this length scale here. That is your lambda minus mk, sorry, further along here. Lambda minus mkk is the eigenvalue minus the diagonal. And this must be less than, if it's equal to, then that means the eigenvalue is sitting on the circumference. Because all the off-diagonal terms, their moduli have been added up to define the radius, remember? Go back here. What did I say? All the off-diagonal term magnitudes have been added up here. That's the radius. The center of the circle is the diagonal term. So lambda minus mkk is your A11. Lambda minus mkk modulus is less than or equal to sum of all the off-diagonal values. All the off-diagonal values is that positive number. That's your radius. Okay? This is your radius. Let me write down here. So this is the radius. It is this radius here. That is your radius here. A11 is here. So lambda minus mkk, that is the radius, is equal to mk, sum over all mkj, k not equal to j. So this whole idea of Gershgorin's theorem essentially then comes from just those few statements that we got to get us here. This, of course, is the whole equation being written up, and then, of course, if it's a steady state, then you have a beautiful condition that emerges. And that condition seems very simple at first, but it's actually very profound. So, because it is the steady state, observe that your P no longer has a time dependence. It's P of L here, and it's P of K here. No time dependence, because it is a stationary state, steady state. And the rate of going from L to K is coming in, and the rate of returning from K to L is coming in. So it turns out that if the left-hand side is 0, because everything is positive, and because you're already sitting in a steady state, you have to conclude that WKLPL is equal to WLKPK for each K and L. So this is a condition that is coming in for the steady state, or let's say the equilibrium state. So in this language, where you are seeing the energetics of the system in terms of state transition, it can be very well applied to a quantum mechanical system as well, to a state transition, then WKLPL is WLKPK. And this particular condition is a very important condition. And it is captured in this statement here called the concept or the principle of detailed balance. The probability of going from one state to the other is identically equal to the probability of the reverse transition. Because it's only when the two transition probabilities are equal and opposite in sign, sorry, are equal, opposite in sign is already built in, will you have a perfectly stationary equilibrium state? So a lot of times people who do stochastics, who do stochastic analysis, statistical mechanicists in particular who do stochastic analysis, they often refer to this condition detailed balance. You'll read papers on using stochastic analysis where they say, oh, this guy is equal to that guy, but this probability is tied in because of detailed balance. That's what they mean. They mean this equation. So it's a very important equation in stochastic analysis. And this equation also has a very beautiful outcome. You see, there is no question that sum of all the probabilities is 1. And that condition implies this. How it implies this, I'll tell you. And why this is important, I'll tell you also. You see, at equilibrium, WL K to L and WL to K should be equal. Now, one case is excluded, that is L equal to K is excluded. So if there are n elements in my matrix, there's WL to K, sorry, K to L over WL to K, sum over all L can only give 1 over n minus 1 because it can't give 1 over n. L is not equal to K in one case. It'll only give 1 over n minus 1. So, and again in equilibrium, you expect probability of getting to the Lth state and the probability of getting to the kth state to be equal. So therefore, if you say that, then P of K is 1 over 1 plus n minus 1, which is 1 over n. Which is what makes sense because the probability of any state is now 1 over n. Every state is equally probable. There are n particles. Probability of any dog barking is 1 over n. All the dogs are equally likely to bark. Right? So, there's a very beautiful problem where all this Gershgorian theorem, this, that, eigenvalues being negative or imaginary, all of that nonsense piles up at the end of the day in the limits to this beautiful, simple result. So there is a lesson here, and I've touched upon this lesson before, but let me do it again. Whenever you set up a physical problem, and you'll be setting up physical problems, always make sure that your limiting conditions are beautifully recovered, because that is the best way in which you can pitch this tent and make it stable. Your limiting conditions got to be perfectly covered very naturally. And this is a problem, this master equation problem with Gershgorian theorem and all that, is where all the beautiful limiting conditions naturally emerge without any trouble. This is the part that I don't think I was able to do. I've already talked about detailed balance and everything. I've just rewritten it here. But this is the proof of derivation of this formula. So this formula that you see, this whole game here. How do you derive this formula? The way you derive this formula is worked out here. This is the formula at the end of the day. This is the formula we used. But we start from the fact that Pj at equilibrium plus Pk at equilibrium, where k is not equal to j. And here, of course, k can be 1 to n, accepting equal to j. Sum of all the probabilities explicitly written up here is equal to 1. We have no disagreement. We already know that sum of all the probabilities here is 1, right? I have just written it up by splitting up the k not equal to j and the k equal to j parts. Now this k not equal to j part from detailed balance principle, I can write as this. This part is from the detailed balance principle. See, this is the part that gave us the detailed balance principle. So WKLPL is equal to WLKPK. That's exactly what I'm using here, excepting I have rewritten it in terms of the P's organized a little differently and imposed that the total probability can't be more than 1 or less than 1, it's equal to 1. So once I've imposed that, then all I have to do is that take this PJ equilibrium out the common. So this one and this one common. And once I take this common, I exactly recovered the denominator. That takes me to the detailed balance. So that's the story here. Actually, my today's plan was to start here. But then as I was, that was what I had planned to do today. I started slide number 172. But then I realized that, my God, over the last, how many days did we not have class? Probably 10 days or so, 11 days. On 10th we met and today is 31st. So 21, 21 days we didn't meet, is it? Oh, 20 days we didn't meet. So 20 days is a very long time for the human brain, you see. So as I was preparing, I said, shit, what the hell was I doing before I stopped? And then oh, do I remember all these things? I went, now I remember. So I figured, I'm sure for Vivek and Tony, they've forgotten every damn thing I've said. So I'm going to start back out over there. So now at least we can reestablish the flow again. So, okay, one thing I have to tell you, because of this Thursday, I have to go to this talk. Thursday, Tony, what is your schedule? Can we start a little early, or you have something going on? Are you working or?
I'm working. We should be able to start earlier though, because I work until noon and then I have my research group meeting 12 to 2, but it never goes the full 2 hours.
Okay. Um, and how about you, Vivek?
Early is always fine for me.
Early is fine. So let's do the following. We'll start, even if we can start 15 minutes early, it'll save us. It'll
Mhm.
give us some time. Then I can close by 3 because I have to drive all the way to the
Yeah, that
recording.
works.
Yeah. So we'll start at 1:45 Thursday. Um, anyway, so let me stop here. Just make sure that you're fully understanding this part, because what I'm going to do next is going to build upon this. And that's the reason why I wanted to go back. I wanted to tell you a little bit about how to construct the dynamics and the statics of a two-state process. Okay. Uh, so essentially what is called a dichotomous process. A dichotomous process is essentially a system hopping back and forth between two states. So imagine two dogs barking, same problem, dichotomous process. Then you can actually work out the time-dependent pieces of it and so on and so forth. I added a little bit of a difficult version of this also, which I may or may not cover because it is not always very revelatory. This is a two-state problem, but I also added the three-state problem. So instead of a two-state, you have three states. That means you have cubic equations. So you can solve it with cubic equations. You can also solve it using the spectral decomposition technique that I was learning about. I didn't use it before per se, but it's very nice. It's a very, very pretty way of doing things. And you can use symmetry, don't have to do such hard work. You can work out, you can actually solve the master equation and not only get the steady state behavior, you can also get the time dependent behavior. So I wanted to kind of give you another taste of this before moving on. And then I wanted to take you to the Markov chain problem. I might add Linda's problem here a little bit, which I didn't think about when I'd forgotten about actually. So here, essentially, it's a problem of a restaurant serving hamburger, hot dog, and pizza. It serves only one dish. So what it serves that day is dependent upon what it served the previous day. The probability of it serving a hamburger on 2 consecutive days is 0.2. Hamburger followed by pizza is 0.3. Hamburger followed by hot dog is 0.5. So if it goes one route, what's the other one? What's the next one? So for example, if it serves hamburger and pizza on 2 consecutive days, you immediately know there's a 70% probability it will serve a hot dog the next day. And there is a relatively small probability it will serve pizza again because there is nothing here. But there is a relatively high probability you can still serve the hamburger back. Because hamburger back is 0.6 and this is 0.7. So using these numbers, you can now figure out if you are going over a span of a year, 365 days of following this rule, what would be the typical probability of it serving whatever on a given day? So for example, after 10,000 iterations or something, here, it turns out the probability of serving hamburger is 0.35, pizza is 0.2, and hot dog is 0.43. Now, you can actually get this estimate not too bad in just one iteration or 2 iterations. So it's like that. I kind of wanted to give a taste of this and then expose you to the battle problem, which, by the way, I've forgotten because it is now about 15 years old. So I have to also read up the battle problem. All right, so Thursday it is. And then we will move on to some dynamics problems again. So okay, so just so that you realize what I'm trying to do, I took you through the main dynamics problem of non-equilibrium StatMech to the extent I can. I did generalized Langevin. Then I switched gears, I did the stochastic stuff. So once the stochastic stuff ends, I'll go back now to the dynamics problem, non-stochastic dynamics problem, but now without temperature. So there are many body problems without temperature, which means there are many body nonlinear problems typically. Okay. So many body nonlinear problems is a fast evolving enormous field. And our understanding of this area of physics is pretty much as good as our understanding of the Big Bang. That means we pretty much don't understand all that much. We understand just about enough to waddle through. But if you ask a mathematician versus if you ask somebody like me who work in this area, our answers would be just about as different to questions as you can imagine. Yet, it's a lot of fun because I get invited typically to go to applied math conferences and speak on my work. And what I learn is to figure out what they're talking about. But all of them can figure out what I am saying. And so it's more gain for them, gain for me, but not as much because I don't understand the language. But this is how it is. And oftentimes, this is not only fun, but in a more serious level, it helps you understand how people think and to be able to relate to each other and build, because unless we can do this basic process, this all happened by very organically for me. I just figured that this is an area I need to study to be able to understand problems of my interest. As a physicist, there are physics problems. The only problem is that all these physics problems have been usurped by mathematicians. which is not atypical. Mathematicians do physics problems usually, but in a different way. And so it is not a surprise. In fact, it's a great delight that they keep inviting me to these talks. And I am the beneficiary of learning to think in a way that I can communicate with those guys. Anyway, so I'll tell you about that. That's how I'll close this this semester, this whole month. After we finish this, I'll take you gradually through a build-up of the phenomena associated with nonlinear dynamics and how bizarre they are, how little we know about them, and how consequentially important they are actually to our lives every day. Every time you take a flight, it's nonlinear dynamics. Every time your plane goes through a bump, it's nonlinear. Every time you cross the Rocky Mountains with the turbulence, it's nonlinear dynamics. So every time you open your tap, it's nonlinear dynamics. I won't go to the tap problem. I won't go to fluid dynamics. I don't know fluid dynamics myself. All right, very good. So on Thursday, we'll start at 1:45. And Vivek, after I get done, I'll put together the list of this. In the meantime, just do it with Fortran. If you can run Fortran, do it with Fortran. Tony and you can talk about it. And I don't think Tony knows Fortran, right?
Yeah, I do a little bit. Yeah.
Oh, you know. Oh, you can also run the Fortran code then. Yeah. Very few people know Fortran these days. So I'm quite impressed with you guys.
I did also move it into Python though, but I do technically know Fortran. I'm just better at Python.
I see.
And
Good. So I think, in fact, Vivek has questions for you then, because Vivek wanted to move the code to Python.
Mhm.
yeah,
Okay.
that's what I'm trying to do actually.
Yeah, we can definitely talk. And then also, I have all of my lecture notes that I took in class from StatMech 1 that I could also send you. So from like a student's
Yes.
perspective, because I do a lot more like explaining and filling in blanks and connecting
Okay.
dots.
Oh, that will
So
be
I
very
will,
helpful.
yeah,
Mhm.
so I will let you know what part I would like actually. So yeah, we
Yeah.
will discuss that in later.
Yeah, sounds
No,
good.
don't do that, because then it will get very confusing, because this whole thing is like a song.
Mhm.
Okay.
The way I cover StatMech is a sequence of chapters that builds the whole story. It's like a pyramid, right? So if you take a slice, then you'll get very lost. But once
Okay.
you go through that, some areas you can go through faster because you may know, right? And some areas you may not know, so you'll go slower. So it's okay, but build a pyramid, because this pyramid is actually sort of consistent with the structure of about 2 or 3 major books, more modern books. That's what I kind of used, because I wanted to give my students a very standard diet. This class, I have a lot of freedom, but there I had to give a very standard, because everybody takes it as a required course. So you will get a full dose, whatever you know. I don't do Lanjavan, no, it's all equilibrium in that. So you may know quite a few things, very fine. So you can go quickly. So Tony, you send me a copy of your version and send Vivek one, and I'll also slowly put together my SatMech lecture notes and give a copy to you. And you already have a copy, I think, to Vivek.
Sounds good. I don't think I missed any classes that semester either, so I should have all of it.
I don't think you did. I don't
Mhm.
think you did. Yeah. Yeah. Okay, good. Take care.
All
Bye-bye.
right. Thank you.
Yeah, good night, guys.
Thank you. Bye. Good night.